Today we're going to be talking about the different gas laws. So before we get into the different laws, we're going to talk a little bit about the background terminology. You can see the underlined words on the page. Those associate with different definitions that go along with this unit. The first one we come to is gas pressure, which is simply a collision of gas particles with an object. It's the force per unit area. A vacuum can be created when there are no or very few gas particle collisions. A barometer is an instrument used to measure atmospheric pressure. Air pressure moves in every direction, so they exert pressure in all directions. This is the atmospheric pressure or air pressure. It's also known as the barometric pressure and sometimes is referred to as the total pressure. Another device that is used to measure pressure is a manometer. It's an instrument used to measure gas pressure in a closed container. Air pressure will differ at different points on the Earth because of gravity. The gravity at the surface of the Earth is much greater. Therefore, the air pressure is less at higher altitudes than it is at sea level. In this diagram, we will look at a device for measuring atmospheric pressure, but before I go into a little discussion about it, I will give you guys a minute to look over the diagram. So after taking a few seconds to look at the diagram, we'll start over here on the left. On the left, we have what looks like a bowl and some type of liquid in the bowl and a tube that is sticking out of the liquid to the right. Usually people use mercury to measure atmospheric pressure. So you can see the pressure exerted down on the liquid is going to force the liquid up through the tube. Now the space at the very top is the vacuum, and remember that's the empty space that can be created where no collision of gas particles exist. So, as the fluid rises, you're able to measure exactly how much atmospheric pressure is being exerted down by the liquid. I'll give you guys another second or two just to re-look over the diagram. So the next thing we're going to talk about is different units of pressure. The SI unit for pressure is a Pascal. Pressure can be reported in the following units: kilopascals, millimeters of mercury, atmospheres, or torr. Any of these units will work when you're doing the upcoming equations as long as you stay consistent with your units. You should know that these values and their conversions. So 101.3 kilopascals equals to 1 atm, which is the same thing as 760 torr, which is also equal to 760 millimeters of mercury. So in the examples below, I'm going to help you go through a couple of them. I will let you try two on your own, and we'll check our answers. So in the first example, we have 3.3 atms, and we're trying to go to millimeters of mercury. So as stated above, we know that 1 atm equals 760 millimeters of mercury. So 3.3 atms, you'll take that and you will multiply it by 360 millimeters of mercury. When you do, you should get 2,508 millimeters of mercury. For the example right below, 745 millimeters of mercury to torr. You notice above that 760 torr equals 760 millimeters of mercury. So this is essentially a one-to-one conversion. So 745 millimeters of mercury equals 745 torr. Now moving to the examples on the right, I'm going to read them aloud. I'll give you a second to answer them, and then I'll go over them. The first one we have is 564 kilopascals, and we're going to atms. So in your calculator, you should have taken 560 kilopascals, and you notice that 101.3 kilopascals equals 1 ATM. So you should take that 564 and divide it by 101.3, and you should have gotten about 5.57 ATMs. The problem below, we have 212 torr and we're going to ATM. So take a second and try to solve that one out. In this problem, you notice that 1 ATM equals to 760 torr. So, you should have taken 212 torr, divided it by 760, and you would have gotten about 0.279 ATM. So the next thing that we're going to talk about is standard temperature and pressure, or STP. Scientists have agreed upon standard gas conditions of temperature and pressure of a gas. These values are: temperature is 0 degrees Celsius and pressure is 1 ATM. Down here we have to have a temperature conversion because all temperatures in relation to gas laws must be converted into Kelvin. So we're going to do a couple examples down here to make sure we understand how to do it. In the first example, we have 25 degrees Celsius and we're trying to get to Kelvin. So you take 25 degrees, place it into your equation, and add it to 273. When you do that, you should have come out with 298 Kelvin. Example number 2. We have 313 Kelvin and we're trying to get to degrees Celsius. So we have 313 equals degrees Celsius plus 273. All you have to do is subtract out the 273 and you should get a degrees Celsius of 40 degrees Celsius. So a little information about the gas laws. They're simple mathematical relationships between volume, temperature, and pressure of any given gas. Some concepts that you should always remember are the following. Your volume always needs to be converted to liters, and below that are some easy conversions for anything you might see when trying to convert to liters. The other important point is to always convert temperature to Kelvin. The last point is that you should make sure all units of pressure are the same. Now notice here for pressure, you do not have to be in any specific one, just make sure that all your pressures are in the same unit. The next thing we're going to talk about is our first gas law, which is Boyle's law. It was came up with by Robert Boyle in the 1600s, and it relates pressure and volume of a gas. At any constant temperature and mass, we can predict how a volume or pressure will change if the conditions change. Boyle's law states that the volume and pressure are inversely proportional. That is, if the volume of a gas increases, the pressure will decrease. And if you take a look at the graph over there on the bottom right corner, you can see that as volume is going to increase, the pressure decreases. The mathematical relationship is as follows. V1 times P1 equals V2 times P2, where V1 and P1 represent the initial conditions and V2 and P2 represent the final conditions. So we're going to look at this diagram right here, and we can see what happens to our pressure and our volume as you either increase pressure or decrease pressure. On the top one, if we follow the arrow, if you increase the pressure, you can see that our volume has been decreased. Whereas the one on the left, if you decrease the pressure, our volume has increased. So I'll give you a second to take a look at this diagram. Next, we're going to try some practice with Boyle's law. So example number 1. A balloon contains 30 liters of hydrogen gas at 100 kilopascals. What is the volume of the balloon when it rises to an altitude where the pressure is only 25 kilopascal? And then it says, assume that constant mass and temperature. So the first thing that I do whenever I do any of these problems is I write a little chart on the left for everything that I know in the problem. So I'm going to go ahead and do that. So right here on the left, I've went ahead and assigned V1, P1, and P2 values. The thing I'm looking for is V2. The next thing that I'm going to do is I'm going to look for what equation to use. Right now we've only learned about one equation, so we're going to go ahead and use our V1, P1 equals V2 P2. Now from here, we're simply going to plug in our numbers. So you can see that I've taken 30 and I've multiplied it by 100, and I set it equal to V2 times 25. Notice that my units of pressure are the same, so we're on the right track. Then from here, I'm simply going to solve the problem. When you solve out the problem, you should have gotten roughly about 120 liters. Example number 2. In this example, I'm going to again read the problem, then I will give you a few seconds to solve it on your own. It says, a sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atm. What will the volume of the gas be at a pressure of 0.987 atm if the temperature remains constant? So remember, number 1, your volume always has to be in liters. Then make a chart like I did above on the left side. So I'm going to give you a few seconds to go ahead and set that up. So you should have had a few seconds to set that up, and you should have set it up like I did. Now, in my chart, you notice that we have 150 milliliters for volume 1, our pressure of 1 is 0.947 atm, and our pressure of 2 is 0.987. Remember that our volume needs to be in liters, so you will have to change this in a second. The simple conversion is that there are 1,000 milliliters in 1 liter. Next, we'll use our equation, the same as we did above, and from here we'll plug in our numbers. Now notice that in this part of the equation I went ahead and I changed our volume. Our volume is now 0.15 liters. So I'll give you a second and you can go ahead and solve this problem. After solving the problem, you should have come up with a volume of 0.144 liters. So the next law that we're going to talk about is Charles' law. Now Charles' law is actually a French chemist, so it's pronounced Charlet, but for simplicity we'll call it Charles. And his law relates to temperature and volume of a gas. At a constant pressure and mass, this law states that temperature and volume are directly proportional to each other. Charles' law states that if the temperature of a gas is increased, the volume will also increase. So taking a look at the picture of the graph on the bottom right, we notice that as our temperature increases, our volume is going to increase. Remember that temperature must be converted to Kelvin. And the mathematical relationship for this is V1 over T1 equals V2 over T2. In this diagram you can see that as we heat a substance, we are going to increase the volume. As we cool a substance, we are going to decrease the volume. So from here we're going to take a couple examples of Charles' law. Again, I will read the problem to you, I will do number 1 with you, and I will let you do number 2 on your own. A balloon inflated in an air-conditioned room at 27 degrees Celsius has a volume of 4.0 liters. The balloon is then heated to a temperature of 57 degrees Celsius. What is the new volume of the balloon if the pressure remains constant? Now remember, I go ahead and I make a chart for everything that I know in the problem. Again, right now I have my temperature in degrees Celsius. You need to go ahead and convert that to Kelvin, which I will do here in a minute. From here, we will write down what equation we use, which is Charles' law. So we see that we have V1 over T1 equals V2 over T2. Next, I'm going to fill in the different variables for the equation. So you notice that I have 4.0 divided by 300. I got the 300 by taking 273 and adding it to 27. And I set it equal to our V2 over 330, which came from 57 plus 273. I go ahead and solve this out, and you should get a volume of about 4.4 liters. For example number 2, I'm going to read it for you. I'm going to give you a few seconds to set it up and solve on your own. So, it says, a gas at 65 degrees Celsius occupies 4.22 liters. At what Celsius temperature will the gas occupy at a volume of 3.87 liters, assuming constant pressure? Now in this problem it does ask you for Celsius temperature, but remember, we always need to convert to Kelvin first. It's just a good habit to stay in. So I will take a second or two to let you guys go ahead and set this up, and then I'll help you through it. So, you should have been able to go ahead and set up your variables like I did above, and there they are. You know which equation you're going to use, which is Charles' law, so we can go ahead from there. And we're going to go ahead and set up our equations so that we plugged in these numbers. Remember that you need to convert the 65 degrees Celsius to Kelvin. So you should have it set up like this. Now take a minute and go ahead and solve. Remember that the answer that you get will be in Kelvin, and you need to convert that back to Celsius. So when I solve this out, I got about 310 Kelvin. Now right here I've subtracted 273 because we remember that our equation is Kelvin equals degrees Celsius plus 273. So I'm taking my 310 and I'm subtracting out the 273 to find my final temperature of part 2. When you do that, you should have gotten a temperature of about 37 degrees Celsius. The third law that we're going to talk about today is Gay-Lussac's law. Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume is kept constant. In other words, if the temperature of a gas increases, then the pressure will also increase. So you can see the diagram of the chart on the bottom left that as our temperature increases, pressure should also increase with it. The mathematical relationship for this law is as follows. P1 over T1 equals P2 over T2. In this diagram, you can see what happens to a pressure as you increase heat. So the diagram on the right, you can see that we've heated up the gas. By heating up the gas, it's going to excite the particles, causing them to bounce around faster, causing more collisions, which increases the pressure. Think about what would happen if you took an aerosol can and threw it in a fire. The pressure or the temperature would increase the pressure so greatly that it would eventually explode. So next we're going to do some practice with Gay-Lussac's law. As we've done so far, I'm going to do the first one with you, and I will let you try the second example on your own. So in the first example it says the gas left in a used aerosol can is at a pressure of 100 kilopascals at 27 degrees Celsius. If the can is thrown into a fire, What will the internal pressure of the gas be when its temperature reaches 927 degrees Celsius? So as always, I like to go ahead and make a little chart on the left of the things that I know. So in my chart, you can see I simply took the variables from the problem and I wrote it out like that. Again, that helps me see things a little more clearly than reading them in a word problem. Next, I write down my equation. So we're writing down the equation for Gay-Lussac's, which is P1 over T1, which equals P2 over T2. Then I go ahead and plug in my numbers. Remember that my temperature needs to be converted into Kelvin. So I took 27 degrees Celsius, I added 273, and I did the same thing for 927 degrees Celsius. I go ahead and solve for my final pressure, and you should have gotten roughly about 400 kilopascals. For problem 2, I'm going to go ahead and read it. I'll give you a few minutes to set it up, and then solve on your own. A sample of helium gas has a pressure of 1.20 atm at 22 degrees Celsius. At what Celsius temperature will the helium reach a pressure of 2.00 atm? Now remember, it's good habit to go ahead and convert your Celsius temperature to Kelvin and then convert it back to Celsius. So take a minute, go ahead and set it up, and I'll walk this with you. So from here, you should have been able to go ahead and write your chart down. You know what equation we're going to use, which is Gay-Lussac's. I'll give you another minute or so to set it up. So when you set it up, you should have gotten 1.20 divided by 295, because I converted to Kelvin, equals 2.0 over T2. When you solve this out, you should have gotten about 491.667 Kelvin. Now remember, your question wants you to put it in degrees Celsius, so I'm going to subtract out the 273 to get a final temperature of about 219 degrees Celsius. The last thing that we're going to talk about in this set of notes is the combined gas law. The combined gas law can be separated so that you can get each of the mathematical relationships that we previously learned. This law expresses the relationship between pressure, volume, and temperature of a fixed gas. The mathematical relationship is as follows. You notice that we have V1 P1 over T1 equals V2 P2 over T2. It is important to note that each formula that we have already discussed can be obtained from the combined gas law if one quantity is held constant. Next, we're going to use the combined gas law to solve the following problems. So just like before, I'm going to do problem 1, and then I'll let you work on problem 2 by yourself. Number 1, it says the volume of a gas-filled balloon is 30.0 liters at 40 degrees Celsius and 150 kilopascals of pressure. What volume will the balloon have at STP? So the first thing I'm going to do is I'm going to write down all the things I know. Remember that STP stands for standard temperature and pressure. So over here on the left, I went ahead and I wrote down in my little chart everything that I got from the problem. My P1 is 150 kilopascals, my V1 is 30.0 liters, my T1 is 40 degrees Celsius, my P2 and T2 were at STP, that's standard temperature and pressure, which is 1 atm and 0 degrees Celsius. Remember that when you do these problems, volume needs to be in liters and temperature needs to be in Kelvin. So I go ahead and I know I'm going to use the combined gas law, which is as follows. From there, I'm going to take all my variables and plug them into their appropriate places. Again, I went ahead and I left my pressure at kilopascals. It was easier to convert 1 atm to kilopascals than it was to convert kilopascals to atms. I also had to convert my temperature into Kelvin. So I have 150 times 30 divided by 313 equals V2 times 101.3 over 273. Now, when I solve these problems, I solve one side first and then I'll solve for the variable. After doing that, you should have, in your calculator, gotten a V2 of about 38.75 liters. Please go back and check to make sure that everything is correct. Now, for problem 2, I will let you guys work on this one after we get it set up. A container with an initial volume of 1.0 liters is occupied by a gas at a pressure of 150 kilopascals at 25 degrees Celsius. By changing the volume, the pressure of the gas increases to 600 kilopascals as the temperature is raised to 100 degrees Celsius. What is the new volume? So, go ahead and write down a little chart of all the variables in this equation. You should have been able to come up with the following chart. I have a P1 of 150 kilopascals, I have a volume of 1.0 liters, a temperature of the first one of 25 degrees Celsius, a second pressure of 650 kilopascals, we don't know the volume of the second part, and a temperature on the second one of 100 degrees Celsius. Remember, when you solve this equation, you will have to make sure that your volume's in liters, your pressures are in the same unit, and your temperature is converted into Kelvin. I'll give you a few seconds to go ahead and set this up. You should have been able to get the following setup. Remember to convert your temperature into Kelvin. From here, you should have been able to solve, and after you solved, you should have gotten a volume of 0.313 liters. Please go back and double check if you did not have time to solve this out on your own to make sure that you can get the same answer. This concludes our slides on the different gas laws.